So we finished our last section by introducing this formal result known as the Wechsler-Zernike theorem, which is a theorem that was established somewhere in the mid-1930s. Now, interferometry has a much older history than that. That predates the Wechsler-Zernike theorem by about half a century. The first practical experiment of optical stellar interferometry was indeed performed as early as 1873 by an astronomer named Edward Stephan, who tried to use it to perform the first direct measurements of angular stellar diameters at the Observatoire de Marseille in 1873 using a telescope known as the Foucault telescope, which was a telescope with an 80 centimeter aperture. And he did so by applying a technique which we now refer to aperture masking interferometry, that consists in masking out most of the aperture of your telescope. So let's see how this works. You know that with a circular telescope, a circular aperture telescope, observing under perfect condition at a point source, a star that so far away that it is non-resolved, that you are expecting a diffraction pattern called the Airy function, characterized by a first dark ring at a location 1.22 lambda on d, where d is the diameter of your aperture and lambda the wavelength of the observation. And this is the characteristic size of what defines your angular resolution with such a telescope. What is happening when you mask out most of the aperture, and the way you would do this is simply by inserting a screen in front of your primary mirror or right behind or in some relay pupil plane, you insert a screen that is occulting most of the aperture, save for one hole of diameter little d. What you've done, what you've achieved in doing so is something that doesn't sound like a good thing. You've essentially killed the angular resolution of your telescope. By shrinking the size of the aperture, you increase the size of the diffraction pattern, which is now 1.22 lambda on d on small d. If the hole happens to be 10 times smaller than the original aperture, then you've reduced your angular resolution by a factor of 10, which doesn't sound all that great. And on top of that, you've killed the transmission of your system by about a factor of 100. So you're losing angular resolution and throughput. Not such a good thing. However, things get very interesting when you start introducing a second hole, or even more in some cases. What you see now is that if you have two holes separated by a distance which we'll call d, or b for baseline, then within an envelope that looks very much like the point spread function of one single, the original small hole, you can see that we recover some high frequency modulations, which we call the interference fringes. And if you look at the characteristic size of these fringes, you will see that the first dark fringe that would somehow indicate of the resolving power of your setup is not at 1.22 lambda on d, but at 0.5 lambda on b, where b is the interferometric baseline, or the distance that separates the two holes. And if you design your mask in not too silly a way, then you can make it so that b is almost equal to d, the original diameter, in which case you've almost boosted the angular resolution of your system by just poking two holes through a screen. Pretty cool. Now, we need to reconnect this experimental result to what we now know about coherence measurements. What is really happening is that at the focal plane of your system, you're combining two electric fields collected that emanate from the two holes that are in your original aperture. you know, if you're looking at a point source, that the light collected by those two apertures is going to be coherent, and so the intensity you're going to measure at the focus of such a system is going to be the intensity of the total electric field. So you can write the equation for the electric field and just develop it using conventional algebra, and you will see that in this expression you find two types of terms. A first term that corresponds to some constant that we would refer to as incoherence, simply an offset to your image that simply accounts for the fact that you've combined the light from two telescopes that throw light onto your detector. On top of that incoherent constant, you find a cross term, E1 times E2 star time averaged, which happens to exactly correspond to the quantity which we've introduced previously as the mutual coherence of the electric field. And if you want to explicit things a little more, you keep in mind that those electric fields are expressed as complex exponentials, and if you explicitly write the product, you will see that naturally out of this simple algebra comes the expression of a cosine function, and the cosine function is the classical oscillating function that explains the presence of the fringes at the focal plane of your instrument. What happens now when we start looking at more interesting things than just single non-resolved stars? Well, let's look at this following situation. We use the exact same setup, a telescope, an aperture mask with two holes, and we first start by pointing at a star. The light propagating from the star hits our two holes, and then from the two holes emanate two electric fields that are going to be coherent with each other and produce interference fringes, just like we described a moment ago. What's going to happen if we introduce a second source, or if we move to a different field where we now have more than one star? And in this case, I've just chosen to represent them using two distinct colors, but they could very well be the same color, those two objects. The light coming from the yellow star is also going to propagate through space, hit our two holes, and the two electric fields corresponding to that star are again going to interfere with each other and produce their own set of interference fringes. We know that the light of two distinct sources, the red star and the yellow star, cannot interfere with each other. We've looked at what we've called spatial incoherence of most astronomical sources. So that means that although we seem to have a problem with four electric fields getting onto our detector, we are not going to consider the possible interference of a yellow and a red beam of light altogether. What we're going to do instead is simply compute the final image or intensity map as the sum of the two individual intensity maps for the red first and then the yellow sets of fringes. So we have sums of fringes, and the result is going to be a function of the exact geometry of the object we're looking at. Here we're only looking at two stars, and so the parameter that's going to matter the most is going to be the angular distance between the two stars. And so if we move it a little bit, like so, or back like so, we see that the two sets of fringes are going to slide relative to each other, and the effect is going to be, if the observer doesn't know that he's looking at a binary star, the net effect is going to be that the quality of the fringe, the contrast of the fringes, depending on the exact location of the two sets of fringes, may simply decrease. And that would mean, from the observer's point of view, who doesn't know there are two stars, that he's simply observing a lower coherence on the target. This is the type of situation you're likely to encounter in this case. Here I've plotted 4 different profiles, intensity profiles for fringes, that kind of fringes, and I've just moved one of the source relative to the other from for different angular separations. And what you see is that for some cases you get, when the two sets of fringes overlap almost exactly, you're going to get the ideal non-resolved. You're not going to be able to resolve that source, and you're going to get perfect coherence. And the first case here, we quantify this the quality of this coherence by what we call the visibility. And here we have a visibility of 0.9, which means that we have 90% of we are 90% the way to a perfectly coherent source. And then we degrade this visibility from 0.9 to 0.7. We simply see that relative to the median profile, the blue line in those plots, the amplitude of the fringe modulation simply decreases to the point where we get at about 0.1 in visibility. And in this case, the modulation, the amplitude of the modulation is really small and very hard to perceive. This is exactly the type of things that Stefan was trying to observe with his experiment. Now, Stefan back then didn't know this, but now we know that the formal relation that links the value of that visibility and the coherence and the structure of the object is the Wenzler-Zernike theorem. Stefan didn't know about this and was simply looking for qualitative changes in the structure of the fringes. He's trying to measure what we call visibility. Let's go back to our point source, because that's the easy thing to understand, and simplify the picture a little bit by removing the envelope effect, and we just have a uniform envelope now, and we only see the sinusoidal modulation, the fringes themselves. We're looking at a point source. We have our two holes, two electric fields propagating to our detector. And if we qualitatively want to look at the fringes, we're going to see that in the dark region of the fringes, the flux count reaches exactly 0 to within the readout noise of your detector, whereas the maximum of the brightest fringes reaches 100% of what you're supposed to get. In this case, we're going to say that the visibility that you get on a point source is 100% or 1. If you're looking at a different object, and in this case we're not going to look at a binary star, but a slightly resolved star. And one way to think about it is to pretend that a resolved object like a big star is essentially made up of several point sources that are right next to each other, to the point where we cannot even make a difference between two distinct objects and one continuous larger object. Because of this, and the fact that you now have the sum of multiple sets of fringes landing on your detector, the net effect you're going to see is that the visibility of your fringes decreases. Like we saw, the amplitude of the modulation of the fringes decreases. And we're going, Wenzler-Zernike would tell us the relationship between the value of this modulation and the size of the object we are observing. Again, the same profiles we saw earlier that essentially tell the same story, except that they look more like the real thing. We still have the envelope of modulation here. So in 1873, Stefan, using his 80 centimeter baseline telescope, and an optical setup that was limiting the separation between the two holes to about 65 centimeters, was not able, although he observed pretty much all the stars he could down to about magnitude 4 with this experimental setup, was not able to directly witness a drop in the visibility of the fringes he got with his setup. And the conclusion he drew out of this was that the stars he looked at had to have an angular diameter smaller than 0.16 arcseconds. Too bad for him. In order to resolve stars, you need to go to larger telescopes, or telescopes that are separated by large distances. And we're going to see how to do that in the next sections.